Hello everyone, and welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on General Physics 1, we want to talk about rotational motion. So to do so, we will introduce something which we call as the angular velocity, angular acceleration, torque, as well as the moment of inertia. So before we get started, all of the notes will be on the description, as well as if you really want more of this videos, please consider subscribing as it means a lot to me. So we will start by discussing what is the angular velocity and acceleration. So the signs of each will be written as omega as well as alpha. So the the same thing in linear velocity, which is basically the change of s over the change of time. You could write the angular velocity, the average angular velocity to be the change of the angle over the change of time. And if you take this change of time to be very small, you would later figure out this to be of delta theta over delta t. This will be the change of theta over the change of time. And this is what we call as the omega. And so there is something that we could actually figure out only by using this. So let's state if you are moving in a circular path and you change for a certain small angle. You would know that this change in the r is basically the radius times the sine theta. That's the change in the r. So if you take this theta to be very small, this will later be equivalent of saying it to be r theta. And so if you actually do much more analysis, if you actually try to divide it over a very small period of time, so you divide it over time, you would figure that this will be the velocity, which is the radius times the omega, which is one of the relation that is used in translating a angular velocity into velocity or vice versa. We could also do the same thing with the angular acceleration, which we will define to be the change of omega over the change of time, or we can write that as the second derivative of the angle. And with the same relation, no, sorry, uh, we could figure out what is the acceleration of the object based on using the angular acceleration. But it is a very special case. So to discuss about this, we will just take this equation that we have already figured out, and we want to try to derive it one more time, which will be the change of velocity over the change of time. This will basically equal to the change of r over the change of time, omega, plus r times the change of omega over the change of time. So this front part is the acceleration, while in here you could see that there's this change of r over the change of time, which is the velocity, or you could write this to be r times omega, multiply that by another omega, plus r times alpha. So in here, you could see that there are two different components when you try to figure out the total acceleration. Well, technically, this is a vector. So if you actually want to do a much more detailed analysis, you would later figure out that this angle and this angle are no sorry this vector and this vector will be perpendicular to each other. But I won't really discuss it here, but you could actually do it if you do the uh, vector calculus correctly. So in here, you need to trust me first that this r alpha is something which we call as the tangential component of the acceleration, while this r omega squared is the radial component of the acceleration. So basically, if you are doing a circular orbit, this tangential acceleration will contribute towards the angular acceleration, while the acceleration going in is the one that is keeping this object in track. So that's the main thing that I want to discuss for angular velocity and acceleration, while on the next chapter I will try to discuss more about the vectors. So after this, we could start discussing about the torque. So we will try to define torque to be R times F. Well, technically, this is if it is perpendicular. So, so, so if you have this pivot here, or this, or this reference point, there is a length R, and then you push this object in here with a force. That means that the torque will be R times F. But sometimes your force could be in this direction. So therefore, you would need to figure out what is the value that you plug in here. So so the way that you will actually do this is by defining a theta, which will be not there. We will define theta from the horizontal line. And so if you try to find this y component, this is the sine theta. So it will be r times f sine theta. And this is the definition of torque. If you actually try to do this using vectors, you will later deal with something called the cross product, which we will later discuss on the next chapter. So, after this, we could start discussing about Newton's law. But instead of doing it with force, we will use it for torque. So, for the Newton's second law, for torque, this will basically mean that it will be a certain inertia, multiply that by a certain acceleration, which we know this to be the angular acceleration, which is the component for the a rotational body. So the question is, what is this I? We haven't really discussed this yet, but if we try to solve this, and let's just assume that the F is perpendicular, so it is going something like this. It is perpendicular with each other, that's R, that's F. We would figure that R times F would equal to I times alpha. And then this F could be written as M times A. And then we would have I times alpha. And we would know alpha to be the tangential acceleration, AT over R. And notice this acceleration is also tangential. So we could write this to be tangential as well. So this will later cancel each other out. And you would later figure out that for a single point, the moment of inertia is defined to be mr squared. And basically, inertia is additive. That means that you could sum up multiple different points to get the moment of inertia of the entire body. The same thing with mass. So basically, the inertia is the sum of the mi/ri squared. Or if you do this with calculus, you would write this as r squared dm. So in order for us to understand this much more fully, we will discuss one of the most important formulas for you to use, which is something which we call as the parallel axis theorem. So let's say if I have an object and I know its center of mass and I am spinning it in the axis that contains the center of mass, and then I know what's the moment of inertia on the center of mass. The question is, if I if I move this axis to be, let's say, in this place with a vector d, let's say, what will be its moment of inertia? Well, this question might seem hard, but if we actually try to understand this much more deeply, we we could develop a formula for this. So, the way that we'll solve this is that we will just assume that we will have a arbitrary point, and so this point here will be described by the r vector cm, while if you actually take it with the reference of the axis that we're interested in, we will call this to be our vector. So basically it's the sum of the ri squared the mi. This ri is this r vector, and this r vector could be written as rcm minus d vector. So we could write this to be the sum of the rcm vector minus d vector squared mi. And so if you remember that if you actually square a vector, it is basically doing a scalar product of it. So basically this will be the sum of the rcm squared mi plus d squared mi plus 2r d let's say dot product, yep, 2rd mi dot product that. So if you actually try to realize this, you would notice that this first part is what we call as the moment of inertia with the reference point of the center of mass. So we could write this as the ICM. You add it with the d squared mi. So only the mi is the one that we need to do the sum because d squared won't be changing. So we could take out the d squared, and then the sum of the small m's will be the total mass, which we will call as the big M. And the last part, minus 2 d vector, multiply that by the sum of mi, r vector. Well, notice this. This is what we know to be the definition of the center of mass multiplied by m. And in here, we know that the position of the center of mass will be 0. So this entire thing will equal to 0. So we develop the idea that ICM plus md squared is the moment of inertia if you move the object within d units. So that's an important thing for you to remember. So there are other things that I want to try to describe, and so if you want to do the derivative, you could actually stay here, but if you don't want to do all of the maths, you could just skip into the timestamp below. So let's start with the very first case, which is the tin rod on its center. So we will have a bar at the center. We define the length to be L with the mass of M. So the way that we will try to solve this is by using the integral. I equals to the integral of r squared dm. So the question is, what is the dm? So the way that we'll describe dm is first by realizing that this entire thing is uniform. So I will define this stick to have a uniform mass. So therefore, if I take a one cut of, so basically if I take a cut of a small piece, its ratio between its dimensions as well as its mass will stay the same. So the mass will be a density, which we will call as the linear density here, multiply that by the length. And so if you take a very small mass, this will be the length multiply that by the very small change, which I will call this to be the d, and here it's the direction of r hat, so it's dr. So doing this, we would obtain that this will be the integral from negative L over 2 towards L over 2. So basically we start from the positions from here towards here, and then the r squared, and the dm is substituted to be the lambda dr. This is dm. And so doing this integral, we would obtain m over L by multiply that by the integral of r cubed over 3, no sorry, r cubed over 3 evaluated from negative L over 2 towards L over 2. And this value, if we actually try to solve this correctly, this will be L over 24, but there's two of them, so that means it's L over 12 cubed. So we would later obtain ml squared over 12. So that's the moment of inertia for a thin rod on its axis. No, sorry, on its center. So what about if we actually ask the question, if we actually spin it on the end? Let's state there. Well, the easy way for us to do this is by using the parallel axis theorem. So we know the moment of inertia from the center of mass, which is ml squared over 12. And so you add it with the total mass, multiply that by the change in distance, which is L over 2. That means it's L squared over 4. This will equal to 3, 4. It's ml squared over 3. So this is the moment of inertia for a thin rod on its axis. So after this, we want to try to solve another case which involves a three-dimensional object. But we will do this with the much more simpler case first. We will have this plate, we spin it something like this, and the dimensions are, this side will be A and this side will be B. So the way that I will try to solve this is by using this same idea. So I will just define this to be the r direction. So for a very small r in here, I will basically try to figure out what's the total mass of this entire slice, which should be constant. So basically, if I have the total mass to be m, this must equal to the density, which I will call sigma because it's a surface density. Multiply that by the total length. No, sorry. Instead of doing that using a surface density, in here we only focus on only one direction. So we will use a linear density instead. So it's lambda, multiply that by the total length, which will be A. And so if we actually try to analyze for a small mass, this will be lambda times dr. So doing the integral again, I equals to the integral of r squared dm. This will later equal to r squared, because the r starts from here, going to a certain point within a distance r, and the dm is lambda dr, taking that to be the integral from negative a over 2, which is the starting point, towards the finish point, which is a over 2. this will equal to the same result as previously, which is ma squared over 12. So that's something unique. You extend the object's width in the actual direction. It doesn't change its moment of inertia, which is which is very useful for you to remember because this will later deal with certain symmetries. So, after this, we will start developing the idea using a double or even a triple integral. So this will be much more calculus based. So we will do the plate again, but now we want to spin it in this axis. So in here it's perpendicular to its surface. And the length here to be A, and this length here is going to be B. So the way that we'll do this is by using the same tactic, defining a very small space there, and basically the entire density must be constant. So we will call this to be the surface density because we are dealing with two different vectors. I will call this to be x and here to be y. No, let's just define that one to be y. So it's m equals to the density, multiply that by the total area, which is A times B. And if you take this for a very small mass, in here the length will be dA and the width is dB. So the length here is dA dB. No, sorry, the area is dA dB. Multiply that by the sigma. So doing the integral, instead here we are doing double integral of the r, but in here the r goes towards this place here, which is described by using the x's and the y's. So in here it will be at the point x and point y. So its length will be x squared plus y squared, the square root and square root that. No, sorry, square root and then square that, which we will later obtain x squared plus y squared. And no, dx dy, sorry. That's dx dy. Multiply that by the sigma, which is m over a times b dx dy. So now we want to set up the boundaries. So in the x direction, it goes from negative a over 2 towards a over 2. So we could write that down. And the same thing for the b over 2. B over 2. So doing the integral, we would obtain the negative b over 2, b over 2. And doing the integral over x, we'll just put the MAB towards the front. We would obtain x cubed over 3 plus xy squared. Evaluate that from negative a over 2 towards a over 2. And you would later need to do another integral in the y direction. This will later equal to, trying to plug it in towards the x, that's a cubed over 12 plus that value a y squared, MAB integral that dy. So we could simplify this to be m over b, the integral of a squared over 12 plus y squared dy from b over 2, b over 2. So doing this integral one more time, we would obtain a squared over 12 multiplied by y plus y cubed over 3. Evaluate that from negative b over 2 towards b over 2. And this will obtain m over b a squared b over 12 plus b cubed over 12. And simplifying this entire thing, we would later obtain m a squared plus b squared over 12. So this is the moment of inertia for a plate spinning on an axis which is perpendicular to both. No, sorry. It it will be on the direction of the plane. No, sorry. It is the normal direction of the plane or the plate. So after this, we want to do a much more complex computation, which will be for a cylinder, for a ring, or for a disk. So we will do the condition for a disk or a we will start from the ring. So this will be hollow, and then if you want to try to figure the moment of inertia for the ring, you could just squash this entire thing down, and then you could do the same type of steps. So the way that we'll do this is by figuring out what is this small mass here with a radius r there, the length of L. So the total mass will later be a surface integral. Well, technically it's a surface integral, but we won't care about this y-axis. So we will do this in a surface. No, sorry, in a linear density. Multiply that by this by the small, no, sorry, by the circumference, which is 2 pi r. And so if you are doubting about this, you could just do this by also defining this this z-axis, but for me I I normally disregard it because in the end there will be symmetries that will later solve for this condition. So for this very small mass here, this will be the lambda, multiply that by the very small change in this, by this very small change here, no, sorry, for this very small length, which will later be described by from this angle theta. So taking this for a small angle, we would obtain that it will be, this is big R, so it's r d theta. So basically this length here would be r d theta. So doing the integral, there is only one variable, so it will be from 0 to 2 pi. So basically it is the entire thetas. So by the way, this will later be lambda r d theta. So therefore, I use theta for my variable. And then for the r squared, it is always constant, so you could write this to be r squared. So solving this, m over 2 pi will go out, and you would still have the r squared, and the integral from 0 to 2 pi of d theta. This will basically equal to mr squared in the end. And that's the moment of inertia for this ring. And now we would do the same thing, but instead we will do this for a solid cylinder or a disk. So doing the same thing, the mass would be the, so technically it should be the volume density but instead I will use surface density of the stop site because it is symmetrical on the z-axis. It has translationally symmetry. So I will use a surface density, multiply that by pi r squared, which is the area of this top side here. And for the small mass, which I will denote this very small box right there, the way that we will actually define what the small mass is by looking at a very small chunk. You could see here, that's a very small angle theta, and then this is the area that I want to figure out. This will be a very small radius vector there. So we would figure this length here to be r d theta, and so we would know this area here to be r d theta dr. And we multiply this by the sigma. So doing the integral, the r would be just r, so it's r squared, multiply that by sigma r d theta dr. And then setting up the boundaries, we know the theta will go from 0 to 2 pi anyways, while the radius go from 0 to the radius. And this will, and so if I do this integral correctly, the sigma is m over pi r squared. So we could just put that sigma out, and inside there will be an r cubed. The d theta will later contribute to a 2 pi dr. So it will cancel out the pi, and so doing this again, this will be 2m over r squared by the integral r to the power 4 over 4, which will be, that will be r squared over 2. So this will be mr squared over 2. And that's the moment of inertia for a disk or a solid cylinder. So after this, we want to use another symmetry, which will be later going to be dealing with a spherical orb. So if I have this ball here, and I want to spin this using the axis, and I will define this guy to be hollow, and it will also be uniform. So the total mass m will be, in here I will define a surface integral. So no, sorry, it will be a surface density. Multiply that by the area of this entire sphere, which is 4 pi r squared, if you know the radius. And so if we want to check for a very small m, this very small m here, this will be, so we will define a very small patch here, and trying to define its lengths. The way that we'll do this is by actually stating this guy to be the change of phi. And so basically this very small bit here will be theta. And so basically this length from this point to this point will be the distance from here to here, which is basically a right angle. No, sorry, which is basically the radius times the sine of the phi. And so if you couldn't really see this, I recommend you to actually to take a multivariable calculus first, so that you could get used to defining these small lengths. So anyways, this is r sine phi, while this length here is gonna be r d phi. No, sorry, this r sine phi d theta. So the total area will be r squared sine phi d phi d theta. And then there's the surface density. So doing the integral again, this will be the integral of the r squared, which is basically the position of of the of the point, which is gonna be r sine phi. So if I do that like that, you can see this one is phi. So it's r sine phi squared, but this r is constant anyway, so it will be big R. Multiply that by the sigma. This is big R squared. This will be m over 4 pi uh, sine phi d phi d theta. So this will be a double integral. And for the phi, it goes from 0 to pi. So we could do the integral from 0 to pi, while the d theta goes from 0 to 2 pi. So solving this, uh, we should be able to obtain the m over 4 pi r squared, the integral from 0 to 2 pi, and then the integral from 0 to pi of sine cubed of phi d theta. So the sine cube will be written as sine phi 1 minus cosine squared phi. So we could solve this. Integral from 0 to 2 pi of the integral of sine phi, which is negative cosine phi. And then this other part, which is the cosine cubed phi over 3. Evaluate that from 0 to pi d theta. M r squared over 4 pi. So all of them don't really depend on the theta. So we could just write we could later write the 2 pi to be outside, because anyways this will later be filtered out and then we know what the value is. So it will be mr squared over 2. Multiply that by the evaluation of this guy. So plugging it in, putting pi, it will be 1. Putting 0, it would be negative 1. So the total will be 2. While in here, it's negative 1 minus 1. So it's 2 over 3. So it's 4 thirds. So this will simplify to 2 mr squared over 3. And this is the moment of inertia for a hollow sphere. So we should do the same for a solid sphere. So for the solid sphere, the only thing that changes will be the small mass, which will later involve this dr. So it will be dr r sine phi d theta, and also r d phi. So for the mass, it will be the density, which we will call as rho. Multiply that by the volume, which is 4 over 3 pi r cubed. And so for a small mass, this will be rho times the r squared sine phi d theta d phi dr. So doing the integral, we will start with d theta d phi dr, r squared sine phi. Substitute the rho, it's 3 over 4 pi r cubed. Multiply that by the r squared, which we, oh, okay. So now the problem is, what is this r squared here? Well, it is almost the same thing, but instead it's a small r. So it's r sine phi squared. So trying to solve this, we could just remove all the constants out. defining the boundaries as well, 0 to pi, 0 to r. This 2 pi would later be able to be filtered out, so this will be later multiplied by 2 pi, integral from 0 to r, the integral from 0 to pi of, let's see here, we still have r squared, so it's r to the power 4, sine squared, so it's sine cubed, phi, dr. So doing the integral now, it's 3m over 2r cubed, the integral from 0 to r of this value, which we have already figured out to be 4 over 3 last time, was it? Yeah, it is 4 over 3. So it is r to the power 4, so basically we can filter out this r to the power 4 outside. So we'll just do the integral from 0 to pi of sine cubed phi, which is 4/3. And so dr. So this will cancel with this, left over with a 2 at the top. So this will be written as 2m over r cubed, and then solving the integral of r to the power 4, it will be r to the power 5 over 5. And doing this will be 2m r squared over 5. And this is the moment of inertia for a solid ball. So all of the moment of inertia of certain objects we have already figured out. And so if you want to actually refer to it, you could just look at it in the description below. So after this, we want to start to develop the idea of the rotational energy. So this rotational energy is basically a form of the kinetic energy which comes from rotations. So I will try to derive this idea. So basically, if you have one particle, this will be just the half dm v squared. And so if you try to do the sum of this, well, technically for a rotating object, this v here will be omega r. So it will later depend on the position. So this will be half dm omega r squared. And so if we actually do this for all of the particles, this will be the sum of the half mi's omega squared r squared. And then we could just put the half outside. We could put the omega squared outside because they will be constant. So we have the sum of the mr squared. And this is basically the inertia. So this is half I omega squared. And this is the kinetic energy for a rotating object. So it's basically it is basically the half mv squared, but using the rotational counterparts. So by doing this, we have figured out that there is the linear kinetic energy as well as the rotational kinetic energy. So if you are dealing with a rolling motion, we could write this total of the kinetic energy to be the linear counterpart, the half mv squared, as well as the rotating counterpart, which is half I omega squared. And sometimes the condition could involve the object to be rolling without slipping. So without slipping, this would mean that the v is the omega r. This is one of the facts that we use if we are dealing with a rolling motion that doesn't involve slipping. So now we want to go into the simulation. But before I go into the simulation, we will just try to solve this problem just by using the mathematics, and then after that we could just look at the simulation to see what it truly means. So, in the simulation, I will focus on a object in a slope, which will be a disk, and it has a radius of r, and there and then I just let it go, and this guy will spin, this guy will roll without slipping, as long as we have a strong friction. So if you actually try to analyze this object, you could just view this body to be a free body diagram of the object here. You would notice that it will have weight, and then it will also have a normal force. But not only that, it will also have friction here. And then this friction would be enough for it to roll without slipping. So the question is, what will be the acceleration of the object, or probably the angular acceleration? So the way that we could actually solve this is by actually trying to use all the ideas of Newton's law. So first, we know from Newton's law that, okay, so this is theta. So this will be theta. So first of all, we would notice that n should equal to m cosine theta. Sorry, the weight cosine theta. Otherwise, it will later phase through the ramp, which is no good. So this is the first condition. Second of all, we would know that the weight minus the friction would later be the m times a. So basically the center of mass will be moving with this certain acceleration defined here. But we know that there's a friction, but we don't know what the coefficient of friction is, or maybe even like how much friction, because static friction involves a maximum point for this force to exist. So there is something else that we should use. And this last thing that we will use is by analyzing its rotational counterpart. So if I define this to be my center of mass, I could see that this normal force doesn't exert any torque, the weight doesn't exert any torque, but the friction exerts a torque, as you can see here. So the torque from the friction is R times F, which is the F of the friction. And this must equal to the moment of inertia of the object. Multiply that by the angular acceleration. So, doing this, we could write the alpha here to be A over R, and the moment of inertia for a disk, or the moment of inertia for a disk or ring, which I already forgot, so I believe in the simulation it is a disk. So we'll just use half mr squared. And then after that, the friction is something that we don't know, and the r is something that we still don't know. So in here, we could cancel out these r's to figure out that the friction should be half times ma. And so figuring out all of, okay. So with this, we could actually figure out that let's see, weight minus friction should be the ma. So the weight is 3 over 2 of the ma. So we could figure out the acceleration is 2/3 of the gravitational acceleration. And so this is the condition for this particular question. Oh, sorry, my bad. This should be W sine theta. My bad. So it's W sine theta. Wait, sine theta. This will be G sine theta. So, so if you just plug in the values in, you would be able to obtain the acceleration of the object. So now we could start looking at the simulation and try to visualize what is going on. So here is the simulation of the rolling motion. So you could see that the object starts at rest, it doesn't move, and then after a certain time, it starts to gain acceleration as it rolls down faster and faster. So you could see that there is the weight vector, the normal vector, as well as the friction vector, which is very small. And and all of this sums up to form this rolling motion, which also includes the torque. So you could see that the only cause of torque is only from the friction, not from the weight or the normal vectors, since they are starting from the center of mass, and then the torque is R times the force, which is always zero. And so with this, you could figure out what the alpha is, and then the alpha relates to the A, and you could see that it doesn't slip while rolling. Therefore, our theory is correct to predict that the alpha R is the same thing as the A. So that's all for this video. I hope that this video helps you. And remember, if you want more of this, please consider subscribing, and see you guys on the next video.